here we see the multimeter. So it's a very useful device. It comes with different functions. So this one can measure voltages, but also currents, resistances. So this cap means that it can measure also capacitance, the temperature if you connect an external probe, the frequency, it can measure the frequency of a signal. So they are I mean of various type, so it depends on the brand. This is a popular device. So you do most of those measurements because you have two leads, the black and the red, and then you go to touch the components of interest with the two leads. So here you have an example of a variable regulated power supply. So this is a double power supply, so you can split it in two like this. So it has two separate sections, independent. Most of the time you see two types of knobs like this, voltage and current. By acting on the voltage knob, you set the voltage you want to have here between the plus and the minus. This green thing, which is called ground, is connected to the metal case, to the body of the instrument. It's not connected to the negative pole of the battery, let's say. This current knob is a little bit misleading. It doesn't allow you to set the current. It allows you to set the maximum current that this device can produce. So let's say, we will see this better once we will study the circuits. Let's say that we can create a short circuit, like we connect a very good conductor from here to here. We set 30 volts, we push the button, and then what happens? So this is a short circuit. Short circuit means that a lot of current can flow in it. We don't want this because it can create problems to the circuit and to the power supply itself. So for this we have this knob. We can set a maximum level of current, and what the power supply will do, it will change the voltage, it will decrease the voltage in order not to surpass this limit that you set. So you cannot control both voltage and current. You set the voltage and you set the maximum for the current. Here we have an oscilloscope. So one important thing to remember is that oscilloscopes are devices that can measure only voltages. So they are very convenient. They are usually like this. Most of the time they have two inputs nowadays. They are called channels, channel 1 and channel 2. So they can record in time the variation of a voltage. So they make a chart. This is time, and this is voltage of time. And you have two separate channels that you can use at your advantage. So you can change the so-called vertical axis amplification. So by acting on those two knobs, you can magnify, you can zoom in the vertical axis, or you can change the so-called time base, the horizontal axis, so you can zoom also in time. You can make this graph being more compact or more expanded in time. I don't speak about the old analog oscilloscopes because they still exist, but nowadays this is what you most of the time will find in a modern laboratory, something digital like this. So you can have other functions. You see here you can select. Okay, here it's in Chinese. It's a little bit difficult to read, but you can select, for instance, the maximum peak. You can click from one point to another one and measure the distance in time. So you can do some measurements, but we have to remember that you can measure only voltages. So here you see an example of a tool for manufacturing, prototyping electronic circuits. So it's a soldering iron. So it's a stylus with a hot tip that can melt the so-called solder alloy, like this one. So this is how it looks like. So this is an alloy of tin and indium. In the past it was tin and lead, but then people found that lead and also vaporized lead is bad for the health, and so then the manufacturer replaced this alloy with the tin indium alloy. So you can fuse this wire, and this can produce the so-called solder joints like this. So you can electrically connect the component by using this melted wire like this through the soldering iron. And as I said just a moment ago, the solder sucker pump is something that when the thing is melted, you can suck it away in case you want to remove a component that you have previously soldered. This operation doesn't work all the time because all this technology has been developed in a way that you solder the components once forever, basically. You're not supposed to plug and replug and plug and replug many times. So here you see instead something different. Particularly this one is interesting for us. So this is a type of board which is called the breadboard. The name is funny, breadboard. I never understood why it's like this. I can show you one in real life. So it's such kind of thing. So here you see I have different components mounted on them. So this is a microchip. These are two transistors. This is a resistor. This small blue one is a capacitor. It's a small capacitor. So this board is not very convenient to produce professional circuits like this one, but it's convenient for experimenting because it's easy to connect components without soldering them, and on this board you can easily put them and remove them and put them again as many times you want. So how does it work? So underneath this board you see there are many holes and you can insert the components here. All those stripes of 5 holes are connected each other. So those 5 holes are connected, those 5 holes are connected, those 5 holes are connected, but all these lines, arrays of holes, are not connected one to another one. So you have a pre-routed circuit, but not completely. So for instance, if I want to connect, now I make some space here, you can see better. If I want to connect this pin of the component, to this red terminal, I can take advantage of this line because those 5 holes are connected together. Then I put a jumper, then from here I go here, and finally I go here. So this processing of connecting things, switching from the description of a graph, which is the schematic diagram, to a real life circuit, is called routing. You have to find a route for your electrons. Another popular thing it's this type of board. This one is also called the breadboard, but sometimes it's called the Vero board. Probably they are all commercial names. So I also have a Vero board here. So this is a piece of Vero board. So you see, you can kind of easily cut it with a saw. So the substrate is fiberglass. This greenish thing is a very good insulator, and it's full of holes which are metallized, sometimes also inside the holes. This one has 2 layers, so each hole is called pad in the electronic terminology, is a sort of island, and you can solder components on them and connect them with wires. I don't know if here I have an example of a circuit like this. No, unfortunately don't have it. Anyway, you can imagine that you can solder pieces of wires. So you put the components like this, for instance. Then with the soldering iron and the solder you create a joint here. Then you can clip the 2 extra part of the terminals on the other side, and from point to point you can go connecting all the things as you need with pieces of wires like these things. So this gives less versatility respect to this one, but a more stable circuit. And here you have the alloy, and one important thing, which is this thing, which is the fluxant. So the thin alloy doesn't melt easily if you don't have a fluxant. The fluxant is a sort of acid which is a little bit embedded inside a cavity in these wires, but sometimes you need more because it evaporates, and so with such kind of pens you can put a little bit of this acid, and this will make the melted thin alloy to become more fluid. So you will wet, literally speaking, the metallic part of the components, and then if you wait a little bit they will solidify in a stable contact. Here we have examples of commercial resistors. So we mentioned already something about the color code for those type of resistors we have seen so far. So these are, let's say, the old style resistors. At that time, during the 80s, they were not able to write little text on such kind of things, so the machines could only write a stripe of color in order to indicate the numeric value of the resistance of the resistor. And the numeric code goes according with a table like this, so you can easily find this on internet, and it tells you how to decode the number of the resistance according to these colors. But nowadays we have other components like those ones that are surface mount resistors. So in the picture here they look like they are big, but in fact they are not, because the picture is zoomed. So I can give you another example of real life SMD components, also for the capacitors, as you see here. So here in this little box we have some components. So for instance, with a pair of tweezers I can take a small resistor. I hope you can see it. So it's pretty small, and on top of it, now the zoom is so small that I cannot go so very far, very close to the camera. So there is a number which tell us the value of the resistance, and similarly for other components like this one. So for instance, this one here, it's a surface mounted capacitor. It looks very similar to the resistance actually, but it's a capacitor. And so on, we can have very small components. And to say the truth, those two ones that I showed you just right now are already obsolete. They are much smaller nowadays. So every year they become smaller and smaller and smaller. So here you have an example of commercial inductors. Again, they can be, as in on the left, so-called PTH, pass-through components. Usually the bigger ones are PTH because they need some mechanical support in order to be attached to the printed circuit board. And here you have a smaller version of the so-called SMD, surface mounted devices. So another thing, here we have very popular cables that you can find in a workshop. So these ones are called alligators. They can have different shapes and size. This one is small one, this one is much bigger. Then a very popular type of cable with a very popular type of connector you can find in laboratory is the BNC connector. Here you have an example. So these are so-called transitions. So these are connectors that changes their type from one to another one. For instance, here this connector, this type of connector, type of plug is called banana. It's called banana because according to some people the opposite looks like a banana. This one is called BNC. And here I have another transition. For instance, I can put it like this, while this type of connector is called RCA. And there are so many of those things in electronics, so without exaggerating, I would say that there are millions of different types of components, connectors, cables, devices, whatever. So here you see just an example of some of them. Another important thing to notice is that nowadays we have a trend from the 90s probably, which is the so-called modules. So because the components are getting smaller and smaller and smaller and smaller and smaller, then for people that wants to use them, this is difficult because really you can't handle them. They are too small. But when you have small things, you can assemble complex circuits that can do many functions, and so circuits will become new components themselves. So here, for instance, you have an example of a module. So this is a battery charger, a complete battery charger in a very thin, light device. So you need to charge a battery. You don't need to design it yourself. Most of the time you go on internet, you find one, you read the datasheet. So you see you have some inputs and or outputs, and the only thing that you need to know is how to connect this and how this thing inside will behave. You don't need the engineers know how the engineers designed all these kind of things. So if you stop to the boundaries of your module and you have the behavioral description, you can use it, even if you don't know how it works inside. So all these things are becoming cheaper and cheaper every day. Okay,